We can represent the carriers on a band diagram, and the simplest band diagram looks something like this. We're going to draw in, this is for silicon, we're going to draw in a valence band here and a conduction band here. The gap between those is the band gap, e.g. just over 1 electron volt. And you can think about the carriers as living on the valence band or the conduction band edge. So in the case of an intrinsic silicon, we're going to take a carrier, an electron from down here, and it's going to be excited up to here. So now we've got an electron sitting in the conduction band where it's free to move. The valence band we can think of as now having a hole in it. So we've created an electron-hole pair. We have still got charge neutrality, but we now have one mobile electron that can move in the conduction band and one mobile hole which can move in the valence band. So the band structure gives us a convenient way of thinking about the where in terms of energy the carriers are, and also where in terms of position. This axis, of course, is energy, and this axis here is position, a spatial location. So in the case of doping of silicon, for example, if we have a concentration gradient of dopants so that we have a lot of dopants on the left and very few on the right, then we can actually represent that by changes in the band structure as we go along the material. So this is the case for the intrinsic carrier. For an extrinsic carrier, we can think of those dopants as introducing additional energy levels which are inside the band gap. So for example, the phosphorus, the donor, will introduce a state in the band gap which is here, and then it's quite easy for that electron to be excited out of that state and for it to move into the conduction band where it's free. So the movement of the electron from this little level here, which is associated with the phosphorus atom, into the conduction band, which is global across the material, that allows conductivity to take place because the electron sitting here had nowhere to go, but once it's up in the conduction band, it's really a free carrier and it can go from one side of the material to the other. So when we represent donors and acceptors in these band diagrams, we can have a donor level here, and we could have an acceptor level there. Of course, these will be in different places because the donor and the acceptor atoms are going to be in different positions inside the material. Let's now be a little bit more quantitative with our band diagram. If the band gap is like this, the band gap is about 1.12 eV for silicon, but for other materials it can be very different. Diamond, for example, it's over 5 electron volts. Silica is about 5 eV. And we typically think of those things as being insulators because there's so much of a band gap from here to here that the chance of a carrier being excited from here to here is very, very low if you're just relying on thermal excitation. And so those types of materials tend to have very, very low intrinsic carrier concentrations, and they will therefore have a very low intrinsic conductivity. However, if you do dope them, you can get conductivity, so there's no contradiction in having high band gap materials which are conductors. It just means that you have to put some acceptor or donor levels near the edge of the band so that thermal excitation can take the carrier, let's say the electron, from here up into the conduction band or to a hole effectively down into the valence band. When we look at dopants added to the band structure, the important property is what's the gap here, the distance between the donor or acceptor, in this case level, and the band edge. Let's look now at where the donor and acceptor levels are in silicon. I've got these numbers here for some common acceptors, boron, aluminum, gallium. That distance between the acceptor level and the valence band edge is 45 millielectron volts for boron. It increases here. Aluminum is 67, gallium 72. And for the common donors, this distance here between the donor level and the conduction band edge is 45 millielectron volts for phosphorus and 54 for arsenic. Now, if you recall that Kt is on the order of at room temperature 25 milli-electron volts, then this indicates that these are on the order of a couple of kT, and that explains why these donor levels or acceptor levels are generally considered to be completely ionized at room temperature. There's enough thermal energy around to promote the electrons from the donor levels up to the conduction band, or the holes into the valence band from the acceptor level, and that means that however many of these dopants we have, that's approximately equal to the carrier density in the material. Before we go any further, let's just think about where these bands come from. If we think about silicon, we've got 3p2 completes it, and these are the ones which are going to make the bands, those 3s and 3p electrons. If we have a separate silicon atom, we know that they have quite distinct energies, and I'll just indicate it here. This is the S level. This is a plot of energy, and this is the P level, 3s and 3p. But as I make the atoms go closer together, this is showing 1 over spacing between the atoms in the solid. We know that as we get the atoms closer together, their energy levels can't be identical. So we have a splitting of the energy, they smear out, and we get this going something like this. And so when we're at this point here, which we can say is the spacing of the atoms in the solid, then this set of energy levels is occupied, and so is this set. And this here becomes the band gap, e.g. So there are 6 possible states for the 3p. We've occupied 2 out of the 6 of them. There are 2 states for the 3s. We've occupied both of them. That's for each atom. And so when we think about what's going on here, this level will contain 4 n states, where n is the number of atoms. And this one also will contain 4 n states. And so we're actually filled all the way up to the top here, but these ones are going to be empty. So in the undoped silicon, this becomes the valence band, and this becomes the conduction band. And so in undoped silicon, all of the valence band is full, and all of the conduction band is empty.